So what happens then? The bar wants to grow, but it can't. It is going to be a perfect fit. So there is no strain. So therefore that's going to be the stress divided by E plus alpha delta T. Well, here's what's cool. We know E. We know alpha. We know delta T. So this is all set up for one equation and one unknown. So this problem statement as it appears is one equation unknown. And so we substitute those in. We've got that sigma. Let's go ahead and write this out explicitly. Notice that when alpha delta T goes to the left-hand side, it becomes negative. So it's going to be minus E times alpha times delta T. And we've got all of those numbers. We might as well put them in. That's negative 30,000 KSI. Notice it's in K. So that means our answer that we get for the stress is also going to be KSI. Then we have alpha, which is 6.5 times 10 to the minus 6th per degree Fahrenheit, temperature change. And then our delta T is 80 degrees Fahrenheit temperature change. So notice the F's cancel, and then we're left with just the KSI. So we do this, we go ahead and run the numbers, and we find then that sigma is equal to negative 15.6 KSI. Or if we wanted to, we could say sigma is 15.6 KSI C. So there is a compressive stress that's generated inside of that axial bar. Now, one of the other ways of looking at this, you can use superposition. What do I mean by superposition? So remember, we've got epsilon total is equal to sigma over E plus alpha delta T. So the superposition is if we apply a temperature increase, this thing grows. So the bar is originally like this. The alpha delta T, it's going to grow. That's what we mean by the alpha delta T, it's going to grow. And then to put it back in its original position, it has to be 20 feet long. We apply a sigma this way. So it needs a compressive stress to kind of cram it back in so it fits in between those two rigid supports. So this applies like so. So this is superposition. In other words, the total strain is 0, but the total strain is going to be a free thermal strain, which is positive, it gets longer, and then a mechanical strain that's negative in this particular instance. Let's go ahead and finish up the analysis then. If we've got a compressive stress, that must mean we have a compressive force as well. So the P that we get, the total compressive force acting on the bar, is simply going to be equal to the stress multiplied by the area. That's it. So we find out that we get a compressive force of 187.2 kips, and that is C, or compressive. That is huge. 187,000 pounds. That is a massive. That is a massive value of force. Now notice also what did not make an appearance in this problem. The given data of the problem, notice the length is nowhere to be found. The 20 feet had no impact. In other words, we would have had the same force if we took 1 inch of bar. So we would have the same stress and force for 1 inch of bar. Exclamation point, because that's a little bit of a shock, counterintuitive. Wow, we're being kind of excited today. Exclamation points everywhere. But it means that all you need is a little segment of material, and it's got a nice snug fit, then you're going to be able to generate a very, very large compressive force if you want to. using a very, very small amount of material. So this problem has a lot inside. It's a lot of activity going along with it, because we've been able to make an observation that we get zero total strain, and then we've realized then that we can use superposition of the mechanical strain, which in this case is sigma over E, and the free thermal strain. So notice a couple of things about this problem. So notice also, you really want to milk this one because it's a great problem. First off, that the total strain is zero. The second is that the thermal strain is alpha delta T always. So epsilon thermal for an axial bar is equal to alpha delta T, and that's positive. Third, the mechanical strain is not zero. Mechanical strain is compressive. So epsilon sigma, it has the sigma value is negative. So we have a value of negative 15.6. So I'll write this as negative 15.6 KSI divided by 30,000. So it turns out that the positive thermal strain and the negative mechanical strain are going to cancel in this particular case. And I'm just going to reiterate that the length is irrelevant. So a lot of interesting things about this particular problem. Now contrast that with the cookie sheet. For the cookie sheet problem, in the oven, 1 epsilon total is not zero. Epsilon total in this case is going to be mechanical plus thermal. Well, there is no mechanical strain in that case. So the total strain is equal to the free thermal strain, which is equal to alpha delta T. The cookie sheet in the oven, the mechanical strain is equal to 0. And so in that case, we have a difference. So you've got to look at the restraint. So we'll say that the restraint is critical. The cookie sheet in the oven has no restraint, so it can expand. And the axial bar that's placed between a rigid foundation on both ends does have restraint. And so it's going to be a big deal for us to be able to determine how much stress is going to be generated inside a particular solid. So this has no mechanical strain. That means that the sigma value is equal to 0 for that cookie sheet problem, unlike the one that we just introduced. All right, well, there's one other fact that we might want to formalize at this point. And let's call this axial displacements thermal effects. Now remember that earlier, the way that we got the axial displacement was to integrate the strain. So I'll bullet that. So recall, we find the delta for the axially loaded bar by integrating the strain. But now we've got an adjustment because the total strain, what we see in measure, is epsilon sigma plus epsilon thermal. So let's remind ourselves again, the total is equal to epsilon sigma plus epsilon thermal. This is sigma over E. This is alpha delta T. And remember, for the axial bar, sigma is P over A, so it's P over AE plus alpha times delta T. So that is going to be the total strain. So now when we integrate that, so I'll put a bracket around this, and we integrate over the length of the bar, like so. What happens then? Well, now we're going to get the total displacement. which again is what we see and measure. And I can really leave this off because that's almost always implied. We always clearly want the total displacement, but we'll leave it there just to kind of emphasize it right now. That's going to be equal to the integral of the mechanical strain, which is going to be P over AE dx, plus the integral over the length of the bar of alpha delta T dx. Now, clearly, alpha could change in part of the bar. Maybe the delta T would change in the bar. But if all of those are constants, so if P, A, E, alpha, and delta T are constants, which they're going to be in most of our problems. So we really just want to be able to practice these things. Then we're going to find that delta total is going to be equal to our old friend PL over AE plus, and then we just take that, the thermal strain, and we don't have to integrate. It comes outside of the integrand, and so we just have plus alpha delta T L. So that is a very useful formula, and I think it's one that you should probably commit to memory. You've already memorized this one. So you have to also add in the alpha delta T L. So again, all you're really doing is you're taking the thermal strain, alpha delta T, and you're integrating over the length. But in this case, we just really multiply it by the length. So this is a good one to commit to memory. And a little bit later in the class, we're not going to do this for a while, but we will actually introduce thermal effects into statically indeterminate axially loaded bars. And so we are going to wait, though, for quite a while before we bring it back in, so you can kind of have a little bit of a break before we introduce that topic. But it's going to be very easy to adjust this. So later, we will use in SI axial bars with temperature effects. And as we start to wind in on 12.5 minutes, we're done with D. And one.